What's the connection to physics? Connection to physics is criticality in physics, which is, so roughly speaking, phase transitions are, happen at a critical point. What are these phase transitions? I hope I'm not offending anyone if I briefly say what they are. The transition between water and ice. Water is a liquid phase, ice is a solid phase, and the transition between them is happening at exactly 0 degrees, given certain temperature and so on. That's a phase transition, and physics knew about phase transitions for a long time, and they happen in in all sorts of areas. So here's an example of magnetism, which is the magnetic property of a material changes when you change the temperature. And roughly speaking, when you heat it up a lot, it loses its magnetic property. What I'm showing you up there on the right is a model of magnetism, but it works incredibly well. It's an easy model. And these black and white squares are now not a computer algorithm. They're representing atomic spins, and the model is spins turn either up or down. And when they're all showing the same direction, then the material is magnetic. Here they're clearly showing in not the same direction, but totally random. Some are showing up and some are showing down. And when I cool this down to a very low temperature, then they do all show in the same direction, or point in the same direction, I should say. And then the material is magnetic. Where is this transition happening? This is not a gradual transition, but it is a sudden transition. And this is represented by the graph on the bottom, where the magnetization is suddenly arising at a particular point. That's the critical point. Okay. And at that point, when we look at in the model, but also this is, experimentally, you can see that as well, we suddenly see something where we would intuitively say this is structure. This is interesting. Right? The right-hand side, that's the broken TV screen. Left-hand side, it's a little boring. In between, suddenly we have, patterns. We have different sizes of regions that are of the same color. So it was this connection between what people knew about, physicists knew about criticality and its relevance in natural phenomena of all sorts, and the sudden occurrence of seemingly the same thing in a computer algorithm. And they thought, okay, hang on here, is nature like a computer? Can we just think of everything that's happening in nature as information processing, for example? And that's where now we have sort of three terms that are being used, well, where people were at least asking themselves, are they the same? And that is criticality on one hand, that is complexity in the sense of these interesting patterns that we see, and information processing. And that's what they were trying to find out starting in the 80s. But it didn't stop there. So once you had this, this linear relationship on a double logarithmic scale in a computer game, then why not look for it elsewhere? And that's what people did. And they went into data from society. So nature and society, I should say. So here is a plot of data from the intensity or strength of earthquakes. And certainly, it's pretty clear that there are few earthquakes that have a massive intensity. So the strength is very high. Most earthquakes, are hardly noticeable. But what exactly is that relationship between the number of them and their intensity? And we see, this is a double logarithmic plot again, and we see it's, at least parts of it are on a straight line. So we have the same sort of criticality behavior, possibly, as we know from magnetism. Other examples that people found at the time, they went into literature and looked for frequency of words, and they saw, oh, look, there are a few words that are used super often, clearly, like the, and, I don't know, whatever. And other words are very rare. That's pretty obvious, but the statistical relationship is again a parallel. So, are our thoughts, are our brains working at criticality? Right. That was the spirit at the time. Is everything sort of self-organized criticality? That's where the term comes from, because the difference is that in the magnetic material, what we have to do to get to the critical point is we have to tune the temperature very precisely. Whereas in the computer game, I was just clicking around randomly, right? And here, I mean, nobody's really tuning anything in earthquakes. They happen at different temperatures, in different geological formations and so on. So it's not just criticality, it's this idea of self-organized criticality that was the buzzword then. Internet servers, which had just started to rise, showed the same statistical behavior. And, more sinister, the number of deaths in wars, so the number of wars that had a certain number of deaths in them. So the questions that people had were, does nature work like a computer? Do nature and society, or humans' life, work following the same rules? Are they all self-organized critical systems? That was the excitement. Okay. And then that's where people thought, okay, however we answer this question, there seems to be something between order and chaos. And that's why sometimes you ask, what is complexity? And the answer is, you know it when you see it. Because we all, we're evolutionarily trained to look for patterns. And that's what complexity is about. It is the theory of pattern formation, self-organization. And so one question that arises then is, how do we measure complexity? We don't want to say, oh, I know it when I see it. Right? That's not good enough. We want to be able to measure it. And then lots of people went along and defined measures of complexity, many of them based on information theory, so entropy, Shannon entropy played a huge role. And I'll just give you one example because it leads us directly back to the logistic map that we saw before, so nonlinear and chaotic systems. This is work by Jim Crutchfield. I did my postdoc with him, so I worked on this for a while. The idea is very simple, and it actually came up in the questions already. What do I need to do to think about complexity? Well, it is about patterns, and if there are patterns, that means there is a certain amount of predictability, right? And what do I need to do to make that prediction? And the idea is really, I just look for conditional probabilities. So I look at a process over a certain amount of time, and then I look at, well, once I've seen, for example, I've seen here a one-dimensional time sequence, I've seen the numbers 3, 1, 4, 1, 5, 9, 2, what comes next? And I just look across this entire time sequence for a long time. If I'm patient, I can collect a lot of conditional probabilities. And then I see, well, after that 2, there are only 3 possibilities. Sometimes it's a 5, sometimes it's a 1, and sometimes it's a 0, let's say. And you collect these sort of equivalences in your prediction, you collect them together. And if this system is totally random, so it's really a coin flip, then your prediction is just as good as a coin flip. So you don't need to collect any memory of the process. It doesn't help your prediction, right? But if memory helps your prediction, then that means there's pattern. And so that's the idea behind this particular measure of complexity. Ultimately, I don't expect you to keep this exactly in mind as all the details, but the idea is the more pattern there is, the more memory I have to keep in mind. That means the more computational architecture really I need to predict something. So it was thought that the if you like, the size of the computational architecture, and that's represented here by 3 memory states, says something about the complexity of your process. Okay. And I think that's still a very, very valid starting point, because the more complicated the pattern is, it's still predictable, but you need to do more work to predict it. Okay? That was the idea. And it worked pretty well. So here is an example of Shalisi and co-workers who tried this out on the 2-dimensional cellular automaton. This is a different one from the game of life. And intuitively we would say, oh, the upper left one, random, not interesting. Upper right one, that looks more interesting. There's certainly pattern there. The lower left one, well, it's still pattern, but it starts to become, a bit random. And the lower right one, that's back to totally random. And then you see that really this measure of complexity captures the in-between. Okay, and it would be, I don't have that example here, but if it was just a white screen, a yellow screen, it would also give you a very low measure. So it's something that people really thought is working out. So then, of course, what happens with a logistic map. So here it's beautiful because you can generate time sequences. We saw that equation earlier on the screen. So what is my time sequence? It's these x values, x1, x2, x3. And of course, it's a deterministic equation. So once I know x1, I can predict x2, and then I can predict x3, and so on. But what if I do this, without knowing this equation? I just look at the time sequence, and I want to predict the next number. And then it turns out that actually, the closer you get to this edge of chaos, which here is very well defined, the onset of chaos is a better term, which is a particular R value, which is on the x-axis here. That's when the system starts to lose its periodicity and it becomes actually chaotic. At that onset of chaos, you see you need a bigger and bigger computational architecture to predict that time sequence, if you don't know the equation. And then once you've passed that threshold of the onset of chaos, then your prediction is as good as flipping a coin, basically. So it was nice because it sort of linked this idea of chaos, complexity as pattern, and computation. It linked it it made sense of them together, if you like. Okay, nice. So with that, we could say, so this work was end of the 80s, so we're now entering the 90s. And there were certainly indications that information processing is highest between order and chaos, so somewhere at the edge. Okay. Now, if you take this and you think, oh, cool, so now I go out into nature and I look at all these pattern processes, pattern formation that's happening in nature. We had an example of, you look, I think I have a picture even. So here are just some examples. What are pattern formations in nature? So on the left-hand side is microbes under the microscope, fantastic patterns that are not static, but they form. And so broccoli at the bottom here and some shell at the top. So these are patterns that are not static, but they, some of them change over time. Are these systems at the edge of order and chaos? That was the idea, I would say, that was around then. And if you measure the complexity, you can say, you can distinguish how far away they are, let's say, from the edge of chaos. And you take these tools from, complexity and predicting time sequences with computation architectures, and you realize it's hard. It's actually not working, and I'll tell you why in a moment. So I'm still convinced that the aim of defining complexity is important. We can't just say we know it when we see it. I like to quote Sean Carroll, who's a physicist at Caltech, who says that many people might not bother to define complexity, thinking that we know it when we see it. And scientists and philosophers have no such luxury. So we really need to figure out what is this, pattern formation in nature, self-organization, what exactly do we mean? And certainly what doesn't work is when you look at this idea of self-organized criticality, this power law, so this linear relationship on a double log plot, when you go out and look at it, so for example, the brain was thought clearly that must be a self-organized critical system, and you go in and you really go and measure it, you see it's not quite working that way. So it's not a self-organized critical system in that specific sense that Bach and Langton and so on were thinking about. So it doesn't match the data that people would bring from the labs.